Very nice case to see principal component analysis, how we find the directions for the principal components using Lagrange multipliers. We will construct a constraint problem and we will use Lagrange multiplier to solve it and show that the solution tells us that the direction of the principal components is in the direction of the eigenvectors of the covariant matrix. Now, this is the constraint problem of the principal component analysis. It tells me that I want to find E, I want to maximize this definition. This is the definition for variance, and I'm not going to get too much deep, but this R is the covariant matrix, and I ask myself in what direction should I look on it in order to maximize the projection of the covariant matrix of the data. So I want to maximize with relation to E. I want to find E that maximizes this, such that it will be a unit vector, because I want an orthonormal base. So I want to solve this constraint problem. I'll use Lagrange multiplying. So in Lagrange multiplier, what I will do is take it and define this thing. This is the Lagrange multiplier formula. We're taking the f of x minus lambda times our constraint. In our case, the constraint is E transpose E equals 1, and the max function is E transpose RE, and we want to max it in relate to E. Here it is, f of E is this, and our g of E is this. In the constraint is C equals 1. Therefore, the Lagrange multiplier function is the objective function minus lambda constraint equation set to 0, so this one, because I took 1 to the other side and got constraint equation set to 0. This is the Lagrangian function. Now, in order to see what is E, let's take the derivative with respect to E. So here it is, the derivative of L with respect to E. When I do this, I get this one equal to 0. We are getting this. And if you look carefully on this, you will see that this is exactly the definition for eigenvalue and eigenvector, where E, which we are looking for, is the eigenvector of the covariant matrix R of the data, and lambda is the eigenvalue. Therefore, we understand that what gives us the maximum direction for the covariant matrix projection is the eigenvectors. And this is how we learn that the PCA, the principal components of the PCA, should be in the direction of the eigenvalues. And now remember that the PCA is defined as the covariant matrix, and the covariant matrix is symmetric. So by the spectral theorem, I can say that every symmetric matrix can have, or it has, eigenvectors. When they are of different eigenvalues, they are orthogonal to each other. Therefore, I will build my principal components in the direction of eigenvectors, which will maximize the variance, as we saw, and the different principal components will be orthogonal to each other. So this is how the Lagrange multiplier helps us understand that the principal components direction should be in the direction of the eigenvectors of the covariant matrix. This was our problem to solve for the PCA, and we solved it and got what we needed. Thank you very much, and that's it.